we discussed the relationship between two sets of data. If the two variables are given as quantitative, we can use a scatter plot, we can use a correlation coefficient, we can use a least square regression line to study the relationship between the two sets of data. How about if the two variables are categorical? Today we are going to use the two-way tables to study the relationship between them. Two-way tables can be given from, for example, block design. Here is an example. We have two variables here. One is the education. The other one is the age group. One is education, another one is the age group. Here, and for the education, we have several variables. The first one is do not complete high school. The second one is completed high school. Next one is college, 1 to 3 years, and the last one is college, 4 or more years. For age group, we have from 25 to 34, and the second one is from 35 to 54, and the last one is from 55 and above. Here, education is called a row column. Right? Means, for example, here, do not complete the high school. We have this number, and this number. Right? For the last one, college, 4 years and or more, and we have this 11,000, 23,000, and 10,000 something. So this is a row, a variable, and the age group is a column variable. And for each number here is a combination of these two variables. For example, the first one, 4,455, means do not complete high school and between age 25 and 34. This is called one cell. Right? And this is another cell, this is another cell, and all numbers here are called a cell. For this two-way table, we can define some distributions. The first one is called joint distribution. Joint distribution. Joint distribution usually is in proportion. So the proportions here, we have a total number of people. The joint distribution means the proportion of this number of the total. So we can use a count or we can use proportions, but most probably we are going to use the proportions. So all this, the cells represent a joint distribution. The next concept is called marginal distribution. A marginal distribution is expressed in counts or percentages. It is a distribution of a single categorical variable in the two-way table. For example, here, the first one we discuss in here, the age of groups. And as we said, we have three groups. The first one is 25 to 34, second one, and the third one. And in each group, the total number of people is, in the first one is 37 something thousand, the second one is 81, and the next one is 56. And we know the total number of people is 175. So if we convert all these numbers in terms of proportion with respect to this, the total 175, so the first group will be equals to like 20%. That is 37 something divided by 175. And the second one is like 45% approximately. That is calculated from 81,000 divided by 175,000. And the last one is this. So this is the marginal distribution for this age group. Or we can do on the right hand side. So the first one, the first variable is do not complete the high school. And this total number, including the three the combination of three age groups is 27 something thousand, and the second one completed high school, again including these three age groups, will be equals 58, and the other two, one is 44, the other one is also 44. Again, the total number of people is 175. And we convert these four numbers into proportions. So the first one, do not do not complete high school, is 27,000 divided by 175, and this gives us like 16 or 17%. And the second is 58 over 175, and that is like 32 or something percent, and the third one and the fourth one. The marginal distribution is the distribution here. The key is the margin. Right? Yes, it is on the margin, on the side. The first one is on the bottom side, and the last one, the next one is on the right margin. So that's easy to memorize. The next important concept is called conditional distribution. This may be more important than the marginal distribution, and it's not easy to understand. And if you are working with statistics, this is very popular to be used. So everybody needs to understand this conditional distribution. Actually, conditional distribution is very general. Right? Almost all the conditions are contingent distribution. So here, the conditional distribution is the distribution for all the variables conditioning on the value of one variable. So here is the condition. That means we know one condition, then we try to find the distribution for all the variables. This is basically the physical meaning for this. Again, conditional distributions can be graphically compared using side-by-side bar graphs, as we discussed on the last slide, of one variable for each value of the other variables. Again, in this example here, in this two-way table, for example, here the condition is in this group, in this age group. And what is the condition is in this group. Then the variable will be the education levels. So for example, the first one, if the age is in this group, this is the condition, and what is the proportion that do not complete high school? Now, if in this group, in this age group, that means the total number, the subcategorical is this one, 37,785. And if you satisfy this condition, then what is the proportion that do not finish high school? Then do not finish high school, and also in this age group will be 4,459. So the proportion will be 4,459 divided by 37785, and this one equals 11.80%. So this is how we calculate the first one. Right? Now, if you are still in this group, what is the proportion that you finished high school? Then the total number is 11,562, then divided by, again, the condition is in this age group again. So on the bottom, that is 37785, and this gives us like 30%. And we can similarly calculate some college or college graduate and all this. All this percentage add up together must be equal to 100%. So this is the condition distribution for this column. On the condition that in this age group and for different variables. Same thing for this one, these numbers. The condition is on the age group of 35 to 54. if you are in this age group, the proportion, for example, for completed college equals the total number is 23,000. So we are going to use 23,000, so 160 divided by the total number here in this age group. So that is 81,000. So 23 divided by 81, and that equals 28%. And we can calculate the conditional distribution for all these condition and for this condition and all these variables. Same thing, we can do this. And also we can calculate it in this way, horizontally. For example, if the condition is do not complete high school, and what is the distribution for these three categories, variables? The first one is between this age group, the second one is between this, and the next one is between this. The condition here is do not complete high school. That means the total number on the bottom, on the denominator, will be 27,000. So for the first number here, you are going to calculate 4,459, then divided by this number, instead divided by this. So we need to know which one is the condition, and which is the distribution. The distribution is for what kind of variable? So here, for conditional distribution, the conditioning is important. We have homework to practice this, so be very careful. It's not very hard, but we need to be very clear about the concept. We discussed the joint distribution, marginal distribution, and the conditional distribution of the same 2V table. Next, we are going to see what's the difference between these three. Here, we have another table. The joint distribution is definitely for each cell. For example, here in this table, we use proportions. So the first one is 1/36. Okay, looks like we have all the numbers are the same. But anyway, those numbers in this table, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, so 36 numbers are all called, combined together, it's called the joint distribution for this variable x and this variable y. So we have 36 numbers in this joint distribution. For marginal distribution, that means, for example, here, the total of all these add up together, we need to add up together. And for this variable here, for this one, the total in this part will be 1/36 plus 1/36 and plus all this together, add up together here, this gives us 1/6. So this is the first one. And for the second one, for this also give us this one. And the next one here is the sum. So we can see all these proportions are the sum of all these different variables. So this 1/6, 1/6, 1/6, all these 6, 1/6 are marginal distribution. Okay? Because they are on the margin, on the bottom margin. And also definitely this part also, this 1/6 is the sum of all this here. So this one, this one, this one, this one, this one, and this one. This form another marginal distribution. So marginal distribution must be on the margin. It is the sum of all the joint distribution on this row or on some columns. The next one is a conditional distribution. Conditional distribution means you need to have a condition. For example, the condition here is 1. You are in this group. What is the probability or what is the distribution for x for in this one here? Because if you are here, that means the total equals 1/6. And this is the condition. This is the condition in here. So the total is 1 over 6. Now on the top, we want to find this one. The distribution for this cell, that will be 1 over 36. So 1 over 36 divided 1 over 6, that is 1 over 6. So this part here will be equals to 1 over 6. How about this? This one is the same thing. So 1 over 36 divided by 1 over 6 is also 1 over 6. And all this will be 1 over 6. Conditional distribution, this is the condition. So we need every one needs to be divided by this one. We can definitely calculate the conditional distribution in this way. For example, for this one, if the condition is this 4 here, the condition is this 4 here, then the total for all these variables will be 1 over 6. All this add up together equals 1 over 6. And what is the distribution here on the condition of this rule? So again, it is 1 over 6, 1 over 36, then divided by the total of here, 1 over 6, and it's also equals to 1 over 6. So this part is 1 over 6, and this is also 1 over 6, 1 over 6, and this is 1 over 6, and all these are equals to 1 over 6. So those are the conditional distribution. So keep in mind, conditional distribution, you need to know the condition first. Then you calculate the distribution of all other variables on the condition of this, on this condition. The next topic we are going to discuss a very interesting thing. It's called Simpsons paradox. Simpsons paradox is association or comparison that holds for all of the several groups and can reverse direction when the data are combined to form a single group. The reason is because of some lurking variable is ignored. For example, we can see if you are good, you are better than me in math, you are better than me in reading, and you are also better than me in science. But in overall, I'm better than you. So this is one example of Simpsons paradox. Here we use this example to see how this works. Look at this example. We have some data. The 2 hospitals treat a patient. The condition of the patient can be classified as 2. The first one is a good condition. The next one is a poor condition. It's very serious. Okay, here are the numbers. For hospital A, if let's see. For hospital A, if the patient is in good condition, the number is treated and 6 died and survived 594. That means the total treated patient in hospital A is 6 plus 594, so equals 600. For hospital B, they died 8 patients and they survived 592. So the total treated patient in hospital B is also 600. Now look at this. So the survival rate for hospital A is 594 divided by 600. And this number is equal to 99%. That means if you, as a patient, is in good condition, you go to hospital A, then 99% will be survived. And the other percent, 1% will die. If you go to hospital B, the survived is 592, then divided by the total, that rate is 98.7. So that is a little bit lower than this one. So from here we can see hospital B is maybe it's not that good compared to hospital A. If the patient is in poor condition, it means very serious. Here are the numbers. In hospital A, they died 57, and they survived 1,443. So the total number of patients in per condition treated in hospital A is these two add up together equals 1,500. So the total survival rate is 1443 divided by 1500, and that one equals 96.2. On the contrary, in hospital B, they died 8 and they survived 192. So the total number they treated is 200. So the survival rate is, if the patient is in per condition, will be 192 divided by the total 200, that equals 96. So compare these two numbers. Hospital A is 96.2 and hospital B is 96. So again, hospital B looks like a little bit worse than hospital A. So no matter you are good condition or you are bad condition, and hospital A is better than B, and here A is better than B. So in each of the categories, good condition or poor condition, A is always better than B. So that's the first one. So here, this comparison holds for all several groups. So this means A is better than B here. Now we combine these two conditions. The total number treated in hospital A is 600, then plus 1500. So the total treated in hospital A, no matter good condition or poor condition, that is 2100. Okay. And they died combined together, 6 plus 57 equals 63, and they survived 594 plus 1443, and that equals 2037. And these numbers for hospital B is the total equals 800, died 16, and survived 784. Now we calculate the survival rate. For hospital A is this one number survived divided by 21, that equals 97%. And for hospital B, that equals this 784 divided by 800, that equals 98%. Now compare these two numbers. A is 97% survival rate, and B is 98. Right? That means in overall, A is worse than B. In this subcategory, A is better than B. In this one here, A is better than B, but overall, A is worse than B. So this is called Simpsons paradox. The reason is because some lurking variable here, a variable that is not, here is just the lurking variable is the patient condition. This one is ignored. So in the combination. So that explains why we have this Simpsons paradox. We have other examples. I can show you another example. This is Simpsons paradox. If you look online, there are a lot of examples. I can give you one here. Okay. Suppose, as we said, we have a test. We have a math. Suppose we have a math. We have a reading, and we have science. And this is my score, and this is your score. Right? In math, right, I did one correct, and I did one correct out of 10. So my point is 10%. And what your performance is, you did all wrong out of 1. So your score is 0. That means I'm better than you. Right? And in the reading, and I did 2 correct out of 10, and you did 1 correct out of 10. So again, I'm better than you in reading. Now in science, I did 10 correct out of 10. So I get 100 points. And you did 18 correct out of 19. So again, you are less than 100, so I'm 100, so I'm better than you. Okay? Now we combine all these numbers together. Out of 30, the total is 30. I did 13 correct. So this is 1 plus 2 plus 10, that's 13 correct. But you did 0 plus 1 plus 18, you did 19 correct. So the total is I have 13 out of 30, and you have 19 out of 30. So you are better than me. So here is the paradox is, I'm better than you in math, I'm better than you in reading, I'm better than you in science, but overall you are better than me. Okay? So this example looks like you are only like 50% better than me. But sometimes this conclusion can be very surprising. So for example, here, suppose we have only 2 subjects. One is math, one is reading. Right? So this is me, this is you. And in math, I did 1 correct out of 10, and you did 0 correct out of 1. So again, I'm better than you. And in reading, I did 1 correct out of 1 out of 10. Right? No, sorry. In the first one, I did 1 correct out of 10. So I get 10%, you get 0, so I'm better than you. And in the second, in the reading here, I did 1 correct out of 1, so I get 100 points. And you did 9 out of 10, so you get only 90%. So again, I'm better than you. But now add up together, I get 2 out of 11, you get 9 out of 11. So you are much, much, much better than me. So in math, I'm better than you. In reading, I'm better than you. But in overall, you are much, much, much better than me. So again, here, the lurking variable is the subject. As I mentioned, there are a lot of examples in the website. You can help you to understand the Simpsons paradox. You can search online.